So in this video, we're going to look at how we derive viscosity, an expression for viscosity. So viscosity, we've said in class, is a measure of the resistance of a fluid to an externally applied shear. And so to set this up, we're going to consider a fluid between two parallel flat plates. So we have a plate on the top, which is being pulled to the right with some force P. And it's moving at some velocity, which we'll call U, capital U. So P here is the force pulling on plate, on that top plate. The bottom plate is stationary, and U is the velocity of the top plate. So what's going to happen to the fluid in between these two plates? Well, we know that by the no-slip condition, the flow velocity at the bottom must be 0, since that bottom plate is stationary. And also by the no-slip condition, it must be U at the top. And so we can draw our velocity profile to look something like this. So at the top, we have capital U, and then we have this linear profile of velocity going down to the bottom. And so this is our velocity profile. U is a function of y. And now you can think about this as having different layers of fluid, and each of those layers is resisting or shearing with the layers next to it. And that is basically a shear stress in the fluid, which is resisting the flow. So we have this shear stress tau in the fluid, which is resisting the flow, which is why it takes some force P to move that plate. So how to quantify this shear stress and relate it to the motion of this plate? Well, we can do that by saying, okay, in some small time delta t, so a very, very short time period, which we'll call delta t, then if we draw a line between the top and bottom plate, this initially vertical line right here, then at some time later, what's going to happen to that line? This line AB in the fluid is going to rotate. Right, the top end of that line will move to the right, and the bottom part of the line will stay exactly where it is. So we'll rotate some angle, which we'll call delta beta, and we can draw that here, some angle, and we'll make that angle look large just to accentuate it. And so that we'll have some rotation of the fluid at an angle of delta beta. And so that means the top, at the top surface, you'll have some distance that top surface or that top fluid will move, which we'll call delta A. Now, in a fluid, the rate at which that angle changes, so the rate at which that changes is delta beta by delta t. It turns out that quantity is proportional to tau, or the shear stress. So if we say that in words, we can say the rate of shear strain, which is what delta beta over delta t is. The rate of shear strain, which we say is delta beta by delta t, or we can also write that as gamma dot, is proportional to the shear stress. Okay, so delta beta by delta t is proportional to the shear stress, but it sure would be nice to have a better expression for delta beta in terms of some of the other quantities that we have here. So that's what we're going to try to do. We're going to try to find an expression for delta beta. So if we look at delta beta, we can see that it's this angle, and if we assume that it's small, that it's quite small, then delta beta is approximately equal to the tangent of delta beta. So again, this is for a very small angle, and we know what the tangent of an angle is equal to. It's equal to opposite over adjacent here. So we have the opposite is delta A, and adjacent here is the distance between the two plates, which is b. And again, this is a valid approximation for small angles. Okay, so now we've transformed delta beta into this expression involving delta A, and we can relate delta A to the velocity of that top plate. In fact, we know that capital U is equal to delta A over delta T. So that's the distance that the fluid is going to move at the top plate over some time delta T. So we can rearrange that and find that delta A is equal to capital U delta T. So then this expression for delta A, we can plug that back in here to find that delta beta is equal to delta A over B, which is equal to U delta T over B. And if you'll recall, what we're looking for was this expression of delta beta by delta T. And if we divide both sides of what we have by delta T, we'll find that we do in fact have delta beta by delta T is equal to capital U over B. So capital U over B is simply the velocity of the top plate divided by the distance. And we can basically say that that's equal to the gradient of the flow, which is equal to du by dy. So that's how much the flow changes between the top plate and the bottom plate. So this is the gradient of the flow, du by dy. So what does this tell us? This tells us that the shear stress in a fluid, tau, is proportional to delta beta by delta t, and we found that tau is therefore proportional to du by dy. And we can even go further than that proportionality. We can say tau is in fact equal to some constant mu times du by dy. And so that's known as Newton's law of viscosity, and it describes the relationship between the shear stress in the fluid, this constant which describes how viscous the fluid is, and du by dy, which is that gradient. So we can also say that if a larger force creates a larger velocity gradient, then tau, the shear stress, will be larger too. And one final note here, relating this back to solid mechanics. So in solid mechanics, we learned that in a solid, the shear stress tau is proportional to the strain. And that is not the case in fluid mechanics. When you have in a fluid, the shear stress tau is proportional to the strain rate. So it's the rate at which you strain that fluid.